Okay, so in this lecture, it's the first time where we will tackle the connection of the Arduino with respect to the outside world. So in the first lecture, we just introduce what is a microcontroller, what's the Arduino, etc. And then in the second lecture, we uh, discussed some of the very basic features of the software. So here, how can we connect the microcontroller to the outside world? So this is really the first interesting part where we will use the power of the Arduino in order to communicate with the outside world. In this section or set of slides, we will talk about the digital pins, so the digital input output, and we will see that a pin can be used as input or it can be used as output, but digital, so either low or high, and depending on the Arduino, low is 0 and high is 5 volts. So each port is treated as a memory location, and all input-output transfers are treated as memory transfer. I want to emphasize this point that I discussed in the introduction, that what's inside a microcontroller is a series of memory places. And one pin that we see is in fact connected to one bit. So whenever I will write a bit on one, this one will be output to the external world, if you want. So this is why we say that all input-output transfer are treated as just memory transfer for us. For us, it's just writing a 1 on a place, and this place, because I know that this place is connected to a pin, that the pin will output a 5 volt. So we have three basic types of registers for these input-output ports. There is what we call the data register. This is where the data is there in order to be communicated to the outside. What do I mean by this? So this is the register where if I put 1, this one will be to the out. If I put 0, this pin will output a ground. If I put 1, this pin will output a 5 volt. So this is the register. The control register is a parallel register that will tell me if this pin is used as input or as output. I will not talk about the status register now. So I will try to find something here. Okay, so I don't know why. No. Okay, I was not able to do this. So here I wanted to show you that for every pin there is a bit that will tell if this bit is 1, I am saying that this pin is an output and the data will be other than this. So for example, if I have 3 bits and in the control register there is 0, 0, 1, so I am saying that the two first pins are output, and the third pin is input, 0, 0, 1. So all of this control register do not tell me what is the level, if it is high or low. It just point out that this pin is used as input or as output. And this is a very important feature in order to optimize the price and the pin count. For example, maybe I will buy a microcontroller for 2 applications. The first application I am using 16 inputs and 1 output, and the other application I am using 1 input and 16 outputs. I will not be obliged to buy 2 microcontrollers. I will buy just one, and I will change the control register by setting 0 for this pin to be an output and 1 for this pin to be an input. And I will tell you how in Arduino we can do this. The next problem, in fact, is the okay, great, this is it. So the next problem is the output latch. We know that 16 megahertz is the clock of the Arduino. Okay, is 16 megahertz. So between one step and the other, it's 1 over 16 times 10 to the power minus 6. So it's around, I don't know, 0 point something microsecond. So it's nothing. In the real world, it's nothing. So if I put 5 volt at one pin for 1 instant, and after 1 over 16 microsecond, I will move to another instruction, and this one that I put on the pin will be removed, nothing will happen in the outside world. I will not see the effect of this in a motor. I will not see the effect of this in a heater. I will not see the effect of this on an LED. 1 over 16 microsecond is nothing. So in fact, there is what we call an output latch. Okay, an output latch is what we call latching the output. It means that there is a feature that will keep this data there until I change it. In other terms, if I put a high on one pin, this high will stay on this pin until I write again a low. So it will not anymore have a 16 megahertz frequency, so this one will not be present only for 1 over 16 microsecond. It will be present for a time where at the end I will change it by writing again a low on the pin. So holding the data in a latch allows the input-output devices more time to examine and respond to the data. So this is why, because the outside world, being a motor, being a heater, being an LED, needs time to respond to data. So I need this data to be latched. So as I said, that all the ports that I have are bidirectional. So they can be used as input and output. Now the thing is that how can I specify? If you recall the Arduino, if you have it in front of you, you see that you have the digital pins going from 0 to 13 in the Arduino Uno. So each digital pin has a number going from 0 to 13. So I will use the function pin mode, and I will specify in the pin the number of the digital pin that I am using, being 0 to 13. And the mode, it can be input if this pin is used as input, and output if this pin is used as output. As simple as this. So for example, if I put pin mode 7 input semicolon, so here I am specifying that pin 7 is used as an input. If I put pin mode 10 is an output, I am specifying that pin 10 will be an output. Typically, pin mode functions is a good candidate to be put in the void setup, because I do not need to do this more than once. So just I will specify the mode, the direction of the ports at once after reset or at startup, and then I will continue the loop, my function, basic function inside the loop. So these are the Arduino 0 to 13 digital input output. So they are 14 pins. Okay, just pay attention that pin 0 and 1 are used also for serial communication. So if you are using any serial communication with any other device, do not use 0 and 1 for normal digital input-output behavior. And I have something else, that pin 13, which is here, is internally connected to an LED on the Arduino platform. What do I mean is this is very important for testing. I do not need to connect any external wires to a resistance to an LED maybe to test something. If I want to test something, I will write 13 high on 13 and the LED will go on. There is an internal resistor and internal connection between 13 and the LED which is on the board. The analog pins here, A0 and A5, as I told you in the first lecture, is that these are internally connected to an analog to digital converter in order to convert it digitally. But why I am explaining this here in the digital input output lecture, because these A0 to A5 can be used as digital input output ports by setting here pin mode A0 input, pin mode A1 output, and in this way you are saying that I want to use these pins as digital input output. Why we do this? Maybe in your application you are in need more than 14 digital input output and you do not need maybe analog inputs. So you will have 14 plus 6, you will have around 20 digital input output. The electric characteristics of these pins those who know me, they know what I'm doing now. Each input-output pin operates on a range of 0 to plus V volt. So a range of 0 to 2 is said to be low, and anything over about 3 is said to be high because it goes into a TTL logic. But this is very important. Each pin can either source or sink. What I mean by source is that positive current, sink negative current. Okay? So it can either source or sink up to 40 milliamp each. So never connect this to a directly to a LED maybe, or directly to a motor. So do not exceed 5 or do not exceed 40 milliamp, or the damage will be large to the microcontroller and to the pin, or even to the device that you are using. So for example, this is two examples on current sinking and sourcing. Look at this. Here I am connecting pin 11 through a resistor to an LED to ground. So here if I send a 0, the LED is off. If I send 5 volts here, so if I send a high here, the LED will be on. However, in this case, I am connecting, so in this case, the current is in this direction, so this is called current sourcing. In this case, I connect the pin to LED in this way, to a resistance, and to plus 5. So if the pin is high, the LED is off, because here there will be no current passing from here to here. If the pin is low, the LED will be on and the current will be sinking. In the two cases, the limit of I is 40 milliamp. So it's really small. So this is why it's important to understand how the connections of the microcontroller pins should be made. So to safeguard against overcurrent, connect output pins to other devices using one of the two components. The first is a current limiting resistor. Of course, we know that if I want to connect something to the pin to any device, I should use a current limiting resistor in order not to have a huge R, huge resistance. Alternatively, so this is the case for LED, for example, we can use transistors. We can use transistors in a way that this is the pin, so this is the transistor, okay? I know that here I can connect anything because I'm taking the current from here to here. So, and the microcontroller is only controlling the base current. And this is a very, very important application in mechatronics systems, where the transistor is used as a switch, and we saw this in many times during the semester, plus during our milestones. So this transistor is only a switch, and the switch is controlled via a microcontroller, sure, with a resistance current limiting resistor. So here, no matter what is the current that is taking here, it's taking from the VCC, so it's not affecting the microcontroller. And this can be replaced, we'll see later on, by maybe a relay, okay, if I have AC or I have large voltages. So these are the two methods of overcurrent protection: current limiting resistor and usage of transistors or any switching components. It's important to remember that anytime our circuit has a connection to ground, that should be common to the Arduino, sure, because the Arduino should understand that. I will go back to the Arduino here. It should understand what is a zero. What do I mean by low? What do I mean by 0 volts? So the ground of the Arduino should be always connected to the ground of the circuit that I am connecting the Arduino to, in order to have a common ground between the two systems. Anytime we use a pin for an input that is not actually connected to anything, it is called a floating pin, and we'll get seemingly random and strange results. I explained this before, that there are 3 states of a digital. We have low, we have high, and we have not connected. Here it's what I call floating. So, okay, if these pins are maybe output, it's not important for us because I'm output from this. However, if this pin is considered an input, I should not leave it floating, because maybe any noise will get a high on this pin, but this pin I don't want to be connected, and this will affect a lot my program. So pay attention. If an input is not used, design your circuit in a way that the pin is not floating, especially if it is an input pin. Okay, so here I go into the strategy. How can I control inputs? And this is something very important. I will explain it now, and you will see that I will be re-explaining it many times after. So in terms of the pin working as output, I do not have any problem in this, because whenever I want this output to be there, I will write a high on this pin, and the pin will be high. If I want output to be low, I will write a low on this pin, and the output will be low. The basic problem is when I have the pin behaving as an input. So how can I test that the input has changed? In other terms, I am waiting for a switch to be pressed, and when this switch is pressed, the lamp or the LED should go on. But how can I know that the switch is pressed? I cannot keep busy just because I have so much other things to do. Maybe I should read the temperature, I should turn on a motor. So what are the strategies? There are two strategies to test the input. The first one is called the polling strategy, and the second one is called the interrupt strategy. I will give you an example, and I always give this example, I like it a lot. Consider that Emil called me and he wanted to come to my house, but I have a lot of work. So I told him, yes, no problem, Emil, pass by during the hour. So I am waiting now. I'm working, but I am waiting for Emil to come. I have two options. The first option is turn on the doorbell. Turn off the doorbell, and every 1 second I go to the door, open it, and check if Emil arrived or not. So I will be working for 1 or 2 seconds, go to the door, open the door, see if Emil is there, close the door, come, work another 2 seconds, go to the door, open the door, check. This is what we call polling strategy. So polling strategy is always checking if the input has changed, if the switch is pressed. So this is the advantage, is that it's very easy and simple operation. Just check if the input has changed. The drawback is that I will go here with the second line, is that the CPU will keep busy checking if the input has changed. For maybe I can, during the hour, check the door 300 times before seeing Emil come. Okay, so I was busy doing nothing, and the CPU will be kept busy just checking for the input change, but the input has not changed. And the other disadvantage or drawback is I am not really in real time. Consider that I opened the door, check if Emil was not there, I closed the door, and at this moment Emil came. So I am returning to work, working for 2 seconds, and then going back, opening the door and seeing Emil. So Emil waited for 2 seconds out of the door. If it's okay for my application, okay. But if I really want a real-time, exact real-time, where every time I touch the switch, the event should be occurring, this polling strategy cannot do a real-time programming. The interrupt-driven strategy is I turn on the doorbell and I will go into my work. I will open my laptop at work, and I will not be keeping myself busy checking the door. At one instant, when Emil will come, he will ring the doorbell. I will interrupt what I am doing and go open the door for Emil. So this is what we call an interrupt-driven strategy, and we will cover it later on. Okay, so today I will explain about the poll strategy. So I will read this slide. Various events called interrupts are allowed to interrupt the CPU as it executes a different task, and it will redirect the program execution. The interrupt mechanism permits real-time events. So here, at the instant when Emil arrived at the door and rang the doorbell, I interrupt. So it's a real time. I interrupt my work and go service this by opening the door. Its only disadvantage is the additional programming and register. Interrupt will be studied in details later in later slides. In fact, in later lectures. So here, let's talk about how can I. Here I have 3 main functions that I will explain. The first function is pin mode, which we saw earlier. It's to specify if this specific pin will be used as input or as an output. The second function is how can I write on an output, and the third function is how can I read from an input. Okay, so the first function is pin mode. So there are two input variables. The first one is pin. It can go from 0 to 13, I said, and from A0 to A5 if I want to use the analog input. And then the state is input or output. So if it is input, it's the input to the microcontroller. So I will connect it maybe to a switch. I will connect it maybe to a sensor, proximity sensor. When I arrive to the obstacle, it will give me high and something will be done, etc. Or in this case, it's high impedance. It's a high impedance because I am getting a voltage from the outside world. In the case where this pin is considered as output, okay, the pin will be low impedance to be able to connect to many other devices. So here I am having just one example. Take this function. For int I equal to 0, I less than 14, I plus plus, pin mode, I output. What's this? Here I am using all 14 pins going from 0 to 13 as outputs. What I can do, I can put 14 pin mode functions, 14 pin mode function, one below the other, or I can do it in a luxury way by doing a 4 function. So here, pin mode I0, so 0 output, 1 output, 2 output, 13 output, and go out. I will set the 14 pins as output. Okay, so the next function is how can I write to an output. So here I set the pin to be an output. How can I write? Basic digital write pin state. So here, after setting my pin, for example, 1 to be an output, I should write a high on it. So I will put digital write 1 high. Okay, so here the pin is the one that you have specified to be an output, and the state is being high or low. As simple as this. So it's digital write. Look at this example. After specifying the 14-bit in the void setup maybe as output, we go into the void loop and see for yourself here. So for int equal to 0, I less than 14, I plus plus, I am writing high on all the pins from 0 to 13. And then delay 1000. We'll explain this more in details, but the delay function is a function that will take an input milliseconds, and the CPU will be kept doing nothing for this delay. So here, delay 1000 milliseconds, so the CPU will wait 1 second, and then I will turn the 14 pins low, and then I will wait 1 second. If this is in the loop, I will go back here and turn high the 14 pins, and then wait 1 second, turn high the low the 14 pins, and then delay 1 second, etc., etc., etc. in a loop. Just a note that even if you will see in the slides or in the code that here I have 0, I'm writing 0, then I'm going here writing 1, then I'm going here writing 2. But in real life, if you are connecting 14 LED to these pins, you will see them go on at the same time, because every instruction will take 2 or 3 clock signals, and every clock signal is 1/16 microseconds. So in real life, you will not see the difference or one LED going on before the other. Okay, and here is the same. The low, basically, you will see all of these 14 LED going low all together. The third function is digital read. So if a pin is considered as an input now, and I set the pin mode of this pin to input, how can I read this value? By doing digital read of this pin. So here, of course, I should put S equal digital read, because this digital read will output either high or low, because it should tell me what is the state of my input now. Is it high or is it low? So this state, high or low, should be put into a variable. Let's see how this function can be used inside an example. Look at this. Sensor state is equal to digital read sensor pin. So consider that, just 1 second, sorry. Consider that I have a proximity sensor connected, so this is a proximity sensor connected to pin 2 of the Arduino, of the microcontroller. Okay, so in the voice setup, I can put sensor pin, it's difficult to write here, is equal to 2. And then I will put pin mode 2 input. Why I put sensor pin equal to 2? To be used here. This is very nice in programming in order to explain to the one or the person reading your program what is 2. I can put 2 here. Okay, this is, if I put 2 here, this is called hard coding. But if I want to soft code, I will put sensor pin equal to 2. In the case, for example, where this pin 2 is damaged, and I want to connect now my sensor to pin 7, if it is hard coded, I want to go into the code, and every time there is 2, I will replace it by 7. However, in the soft coding, I will go into the void setup and replace the 2 here by 7, and this is it. Okay, so it's easier, and I will understand. For example, I can put temperature pin, proximity pin, to understand which sensor is connected to what pin. So take this case here, sensor state, this is a proximity, so it gives me high or low depending on the obstacle that I am facing. So sensor state, this is an integer also, or a boolean, or an integer, it depends, also defined in the void setup function. So sensor state is equal to digital read sensor pin. So here I am testing, is it high or low, and I am putting the state inside sensor state. And now I can do anything I want. Here, if sensor state is equal to high, digital write on let pin high. So if the obstacle is close, let an LED be on, for example. So here I am writing on LED pin high. Sure, we do not forget to define LED pin here and doing pin mode LED pin output, okay, in order to do this. So now I will, and if all of these instructions are inside a void loop, so even if I am still very far from my obstacle, in other terms, Emil is not yet on the door, I will check. So the CPU will be always busy until I approach, and all of this are low, then this condition is not true, nothing will happen. Low condition is not true, nothing will happen. And there is a loop here. Until I approach the obstacle, when I arrive to this critical distance, the digital read will give me a high. Now this condition is verified and the let pin is high. This is the polling strategy on the input pin, sensor pin. Okay, this is another optimization if you want. No need to create maybe here an integer sensor state. I can put this digital sensor pin directly here. So this will be removed and this will go here. So I have if digital read sensor pin equal to high, do directly. This is another way of writing this code. Okay, so what I have is state change now. So here I want to give you an example that will be used many times, because maybe what is important for me maybe is not only about the state of the pin. What is important for me is to detect when there is a rising edge or when there is a falling edge of the signal. Okay, so this is in order to directly check if the state changes from low to high or from high to low, depending on what I need. Okay, so this is what we will call edge detection. Let's see this example. Okay, so here, okay, I have to, this is really a complete example, so I want really to take some time in order to explain this. So first I am connecting a switch to the input pin 2 in this way. Look at this way. So here, because as I told you, I can never leave an input pin floating. So I should have, when the switch is open, pin 2 is 0. And when the switch is closed, pin 2 is 5. Okay, so here I connect switch 1 to pin 2. And from now on, I will call pin 2 switch pin. I created an integer for it, أكيد, because I need to specify to the Arduino how much in memory this will take. Here I'm telling the Arduino, please take 2 bytes, because this is an integer. What is const? Const is constant. In this way, if any time during the code this switch pin changed, maybe by mistake, أكيد. So if I put here switch pin equal to 4, it will give me an error because I created it as constant, so it will be never changed inside the code. Okay, so this is one. Number 2, as you can see, all these definitions are outside the void setup and are outside the void loop, because these can be used here and here. Because if I define these inside the void setup, they will not be known inside the void loop. So I will put them outside the 2 functions in order to be global for the 2. I create state, I create last state, I created let state. Then I created let pin. Why 13? Because you know that, and I have told you that pin 13 of the Arduino is internally connected to the LED which is on the Arduino board. Okay, so this is in order to have some testing without adding connections with the outside world. So I started with void setup. Here I am specifying that pin 13 will be an output because it will be connected to 13. And here I'm specifying that pin 2 will be an input because the switch is connected to pin 2. And I close setup. I do not need anything else from the void setup. Here in this case, I specified the direction of pin 2 being an input and pin 13 being an output. So look at this void loop here. So here, state is equal to digital read of switch pin. أكيد semicolon. So here, what I'm saying is that I am reading the switch pin state, okay, from pin 2 in this case. I'm putting it in the state. No matter what is the state, I don't care now, okay? If state is not equal to last state, okay, so here what I will do is I am testing. If my current state is not equal to my last state, so this is where I have read my pin. So this is point 1. Okay, this is where I have read my pin. If the last time I have read the pin was here, so my state is equal to the last state, nothing will happen. Okay, nothing will happen. So this if will be closed here, and I will write LED state. So I will write maybe high, for example, here on LED 13, delay 20 microsecond and go back. Nothing will, بعد نرجعت, I have read here my state of the pin, nothing will happen, so it's still high on the LED, delay, etc., etc. However, if I have read this one here, but the last time I have read it is here, so my last state is equal to low and my state is high, this if condition is verified. High is not equal to low, I go here. Now, if my state is equal to high, put high in the LED, okay? Sorry, if my LED is high, put it low, else put it high. And what I do now is I will rename or re-put a value inside the last state. Now my 1 here will become my new state. And I go here. I will explain this now, but wait till just I'm explaining the last state now. Okay, so I will re-explain this. If my 1 here is different than my last state here, I go inside. So here what I am doing here at this particular point, I am doing an edge detection. Here I am saying there is an edge, because even if I am testing here my state and my last state was here, also I am finding an edge. So this is an edge. Okay, now if state is equal to high, here what I am testing, here I am finding a rising edge. Because my new state is high and it is different than my last state. So this is here, I will go into, and I am detecting now a rising edge. Here, if I have written if state is equal to low, so now I am detecting a falling edge. Okay, so it depends on what I need here. So if I detected, so I will just let me see, how can I say this? Okay, great. So if I have detected now a rising edge here, I have detected a rising edge. Here I am saying if my LED was high, set it to low. And if it was low, it means else, set it to high. So what I am doing, I am toggling my LED. If it was high, it will be low, and if it was low, it will be high. And now I am digital writing on 13 my new state, either high or low, depending on what is inside here. So if I want to explain this code, I will say that this code will toggle an LED at every rising edge. It will toggle an LED at every rising edge. Okay? So this is the first sketch that you see. I understand maybe you will not directly get the idea, but from experience you will see that this is a very simple sketch. Let's see another example. Also, here I have constant integer switch pin equal to 2, constant integer let pin equal to 13, int state, int last state. I added an integer called button counter equal to 0. And in the void setup, I put pin mode of switch 13 being an output since this is connected to the LED, and pin mode switch 2 being an input since this is connected to my switch and I need it to be an input. State equal digital read switch pin. So here I am reading from switch pin. If state is not equal to last state, so here I am doing an edge detection. And if my new state is equal to high, so here I am detecting a rising edge. In the previous example, at each rising edge, the LED was toggling. Here, at each rising edge, the button counter is increased by 1. So it was 0, now it will be 1. Then last state is equal to state. Then, if button counter percentile here this is the modulo. يعني if button counter modulo 5 is equal to 0, in other terms, if button counter is a multiple of 5, go inside here. So here button counter for this case is still 1, so I will not go here. Else, I will go into the else then. Digital write on 13 low, keep the LED off. Then I will go to the loop. Now, when the switch is pressed again, so there is another rising edge, the button counter will be 2. LED will stay low. Third times, switch, fourth press, fifth press of the switch, my button counter now is 5. Now, if button counter modulo 5 is equal to 0, so it's multiple of 5, go here and write on let pin high and delay 20 milliseconds and then come. So what I'm doing here is that my LED was here on, before was on at every switch, at every rising edge. It was toggling. Here, every 5 times it will go on. Because the 6th time, it will go low. Because 6 modulo 5 is 1, so I will not go here, I will go here. So at the 5th press, it will go on. At the 6th, it will go off. At the 10th, it will go on. At the 11th press, it will go off, etc., etc. So it's a kind of counter, but it's one of the applications that we can use. So in this way, we will finish the digital input-output. So today in this lecture, we have covered the 14 digital input-output pins of the Arduino and the 6 analog input that can be used as digital input. We have seen how to specify that this pin is used as input or as output by using the pin mode function. If it is used as output, the digital write function will be used, and if it is used as input, we will use the digital read function. And we explain in the case of input, we have 2 strategies to take. We can use the polling strategy, which we show 2 examples on it, or we can use the interrupt-driven strategy that we will explain in details in later lectures.